minutes so that he has 5 minutes left to answer your questions. Welcome.
Thank you. Good morning, everybody. Kia ora. I will be talking about that kind of data. So I will show you about the detail later. And in this talk, I will be introducing ChOWDER, a web-based scalable display system which we developed. It's generally called as a type display system. And we have introduced the 3DWebGIS distributed rendering function in the FOSS4G ASIA last year. And today I will introduce that functionality briefly. And we will introduce the massive R-scale the point cloud data rendering case by using ChOWDER. The cloud data captured by the weather satellite and converted to 3D tiles data, point cloud data, was used. And lastly, we will discuss about some technical difficulties and the future work. So let me introduce myself. I am Tomohiro Kawanabe from the Riken Center for Computational Science. Our facility is operating the supercomputer Fugaku, which was the #1 in the top 500 supercomputer ranking in 2020. And now we are ranked at #7 in the latest ranking. And I'm working as the researcher and in charge of software R&D to improve the usability of supercomputers. Last night, I went to that place. Did you know what happened?
Did you?
But tickets were sold out.
Yeah.
Yeah. I was listening then the music and outside. Yeah.
Don't point anything.
It was very fun.
Getting deafened.
Oh, really? Yeah, it was a memorable moment for me. And joke aside, and background and motivation, as you or you know, data is increasing day by day, and it has become common practice to build data in summarized form. As for example, Japan has the weather satellite named Himawari, takes an 11K by 11K pixel images every 10 minutes. So you can see on the web the Himawari's picture like this, but it's summarized. So we think we need more pixels on our displays. And we have issues on the hardware side. The maximum practical resolution for desktop display is around 4K to 6K recently. So, and if you have the expensive NVIDIA GPU, you can use the NVIDIA Mosaic system to combine the multiple display with up to the 16K resolution. But it's too expensive just to get more pixels. So we think we need more pixels at an affordable price. That's why we developed ChOWDER, the cooperative workspace driver. It's a web-based scalable display system for the team discussion and other purposes. And you can get ultra-high resolution pixel space by combining multiple displays in tile form that shows full-screen web browsers. That means we use only ordinary web browsers. We don't need any special software and hardware. And this is the displayable content type on ChOWDER. We can render image, text, the movies, the webcam, PDF, and screen share from your laptop. And also, we can render 3D WebGIS function. Here we are explain about the BDA concept. The ChOWDER operates on a unique concept called BDA, Virtual Display Area. To explain briefly, you can create a tiled display by arranging multiple multiple browsers, logically in the virtual two-dimensional pixel space managed by ChOWDER server. And if you want to put the content to be displayed on that BDA, the corresponding displays will render it. And 2020, we developed the 3DWebGIS viewing function like this. This picture shows an example of viewing the 3D GIS by ChOWDER on 20K horizontal resolution type display system, which consists of 15 of 4K displays. Here I will mention again that each display shows a web browser window in full screen mode running a WebGIS application. This is a diagram of our facility. We have 15 4K displays, and each display connects to a single Windows PC. And we have the map server for the performance test, and we have ChOWDER server here. And this is the rendering result of the 3D tiles object on 3D GIS viewer. And the building data are provided by Japan's governmental project called Plateau as an open data. And today I will introduce the function for displaying Earth level point cloud data like this. Before that, I need to explain how to distributed rendering works. To display the 3D content on a distributed display should be divided its view frustum like this. The left side figure shows a normal view frustum for rendering 3D graphics on a single display. The right one here divides 3 frustums for 3 distributed displays. So we want to do like this to render 3D GIS on ChOWDER. And we found that the 3JS, a library of JavaScript, has an API that enables to offset of that view frustum. And we found that iTowns, which is open sourced the WebGIS developed by IGN France. It's built on the 3JS, and it enables the camera offset API. So we decided to use iTowns as a middleware to develop the distributed rendering function on ChOWDER. Here we explain the sequence of 3D WebGIS rendering. First, GIS application developed for ChOWDER, which is based on iTowns, I mentioned earlier, is launched on the controller client here. The GIS application access to a map server on somewhere on the internet and display the map like this. And next, the ChOWDER server is instructed from the controller client to display the GIS application on the BDA. At this time, the map data itself not sent. Only metadata such as the display position on the BDA and the URL of the map data. The ChOWDER server forwards these metadata to the display clients, and each display calculates the offset of its own view frustum, and based on that metadata, and finally the display client connect request to the map server the map data which is on their view frustums and render it. As I explained here, it was implemented efficiently, minimizing communication cost and rendering cost. This is pros and cons of this distributed rendering function. Pros, number one, ultra high resolution content can be rendered. And second, the application memory can be distributed. Ordinary web browser has the maximum user heap memory limitation, and it is the 4 GB. So distributed rendering avoiding the memory limitation issue with the large 3D data, because the 3D data is the distributed each displays. And rendering cost can be distributed. 3D graphics need computing power. It means the computing time. So if you have the high performance expensive GPU, the computing time can be reduced. But using our system, the practical useful for less powerful GPU. And cons, the network traffic volume is increasing relatively to the normal, using single web browsers. Because adjacent display load data overlapping areas, so we load the excess data. I will skip this part because I don't have time. So this is about data. As I mentioned earlier, the Himawari is the satellite with a satellite operated by Japanese government, and capture images of the Asia and Oceania region every 10 minutes. And it's geometrically collected data is published by the Chiba University, Japan, and it includes the cloud top height data and cloud thickness data on each 3000 by 3000 grid. And we convert these grid data to the 3D tiles. First, we define the voxels from each data grid, and with the cloud top height and cloud thickness data, and we generate 100 points randomly in each voxels. And we use this workflow to convert to 3D tiles, and as a result, we generate the 3D tiles point cloud data like about 6.1 gigabyte and 75,000 files, and it has 8 levels of LOD. And this is the viewing result, 3D representation of typhoon clouds by point clouds. The color of that each point represents the cloud height. Whiter is higher. And this is the actual footage using the distributed rendering function with the typhoon cloud data. Now I am going to dive into the eye of the typhoon cloud. It takes time. And now I adjust the position and sorry for the poor video quality, and adjusting opacity to land island, but I couldn't find the island under the eye. And now we are diving into the typhoon cloud eye, and look around the edge of the eye under that cloud, and back to above the cloud. Yes. This is the difficulty in displaying the R-scale point cloud. As you can see here, and everywhere, the triangular artifacts appears. It appears almost every time, everywhere, and it appears on both iTowns and Cesium. Yes, I tested this data on Cesium. So we found that the issue results from both the data and the application. The codes and solutions for these triangle artifacts. Firstly, on the data side, the coordinate system issue during the data conversion. The iTowns and also the Cesium, the uses a Cartesian coordinate system with the Earth's center as origin, like this. So defining the 3D tiles box, bounding box along these coordinate axes, the bounding boxes on the Pacific Ocean intersect with the Earth's surface in a triangular shape, like this here. And we have also the issues on the application side, that when the corresponding LOD point cloud data is not displayed correctly, as a result, the triangle holes appears like this. So generally, the tile which requested may not loaded, and a common problem on the WebGIS, not only in iTowns. So we think solution is that the bounding boxes that along the Earth's surface should be defined. So the intersects may not happen. This is the future work. We will define the 3D tiles bounding box along the Earth's surface, as I mentioned the previous slide, the expectation for the reducing artifacts. And we will do the performance comparison of 3D tiles, pottery, and COPC. And we have done a preliminary experiment, and it showed the pottery to the fastest. But triangular artifacts appears in all formats. And lastly, the 3D cloud structure accuracy. The point cloud data presented here does not represent a scientifically accurate cloud structure because we generate a point randomly. So next generation Japan's weather satellite will be able to perform 3D measurements. I don't know how they do, but it's enabling more accurate cloud reconstruction. This is my last slide. What time? It's good. I will conclude in this slide. We introduced ChOWDER, a web-based scalable display system, and its 3DWebGIS distributed rendering function. The 3DWebGIS distributed rendering function effectively displays R-scale 3D tiles data and can overcome the web browser's heap memory limitation. The gaps in triangle can appear when drawing point clouds. However, this issue can be improved by redefining the bounding box to follow the ground plane, the Earth plane. And lastly, the ChOWDER is open source software under the BSD2 license and on the GitHub here. So if you are interested in our product, please push the star button on the GitHub. That's it. Thank you. Tena Koto.
Now, if you want to ask a question, I have to give you the mic because otherwise we don't get it recorded. So who's going to go first? Yay. Thank you.
Thank you. It's very good. Like I've been working with, I guess, CCM and big visualization stuff. A lot of the render, I cannot see all of the pixels, right? So I guess this display is not meant for individuals. It's meant for groups, because the individual eye has the fovea and you can only see a little bit, right? So great to have a solution. So what do you think is the actual real use case for this? Just conference areas, big, yeah.
Yes, it will be in the conference area is useful, but we mainly develop for for researching purpose. I mean the researchers gathering in front of these facilities, and you can to close and see the details, and you can from the display and see the whole images. You can use your body to summarize data and the details data. It is not difficult. It can't be do like that in a single display, because the resolution is limited.
Yeah. So you integrate using your body. Interesting. Okay.
Anybody else got a question? No? I'm sure Tomo will be happy to talk at the next break. Oh, sorry. Yes, we have questions. I'll phrase it.
I was wondering how scalable this is. Like, how many, like, at what number of displays would this start to stop working?
It depends on the network bandwidth.
Yeah.
Yes. We tested with the 34K displays, and it works well. The logically, the unlimited. So I think the limitation is the network bandwidth. But we didn't do that because we need money for doing that.
To buy displays, yeah.
Speak to the display vendors, like, and network vendors.
Yes.
Okay, if you'd like to join me in thanking Tomo.